Okay, welcome everybody. I hope you can hear me. If not, just shout out and I will try to change my settings here, but I think it's okay. So today's lecture will be two parts. So one part will be looking at the built-in functions of Python, and the second part will be an overview of object-oriented concepts. So this course will not teach you all the things about object orientation, but give you an introduction on object orientation in Python and how you can use it in a high-level way, and also how to use the objects that are built in. But let's start with the system functions. So Python is a bit special language in that sense that it comes with a really large runtime library. So many other languages, they have very limited runtime libraries, but Python often is going to have the batteries included. So a good kind of rule is that before you get an idea to kind of write a routine yourself, look into the runtime library and see if you can find a function there, because they often are built-in functions for solving most of the problems you have with accessing the system and file manipulation and so on. So we'll start with some of the system functions that are built in. So in many operating systems, you have what's called environment variables. So for example, on Aurora, when you do computations, when you log in, there are a lot of variables set in the terminals and in the system that control different things. And one of the important ones is, for example, path, that controls the search path for where the system will find binaries and so on. And if you need to kind of access environment variables in Python, that is actually built into a special module called OS. And in that OS module, there is a special variable called environ. So it looks something like this here. So you have OS is the module name, environ is the variable containing all the environment variables. So if you want to print out the path variable, you just specify the variable you want to print here in the brackets. It's the same thing when you access a dictionary in Python. And it's also possible to iterate over this environment variable to kind of get all the variables you require. So in this case, I do a for loop here with for variable in OS environment. So it's a dictionary. And here you can print the variable name and also the value here of the variable. So in this print statement, I printed the contents of the variable. It's also possible for Python to do to set your own environment variables. So basically, you do the same thing as you do with a dictionary. You assign the variable name here between the brackets, and just assign it a new value here, like that. And then it's available in your process to use. It's probably not available when you return from that routine, but it's available as long as your Python code is running. So for example, if you start other processes from your Python code, that environment variable will be available for them as well. So if I run this here, we can start with the beginning here. So here you see the search path I have. This is the search path on the Google Cloud instance. So it's not Aurora here. And the next part, I looped over the variables here to print out the environment variables available in this machine. So you can see you have env, you have CUDA versions, you have the search path, and a lot of other variables. And here you see my test value I assigned to my environment variable. You can also get this information in other ways. So the problem with environment variables is that they are system specific. So if you query an environment variable on Windows, it will return you the search path in Windows syntax. If you do this on Linux, the search path the variable path will be different. So if you want to access the search path in a more platform neutral way, there is also a function in OS called getExecPath. And it's a bit different than the other one. So this will list the paths separated here on every line here. So it's of course there are system paths, but they are not delimited with system specific delimiters. And this will work on both Windows and Linux and Mac. When you're running your code in Unix and also in Windows, there is a concept of a current working directory. So when you, for example, open a terminal on Windows or Unix, you can cd to a directory and run your Python code. And the directory you're executing your code is your current working directory. And you can query this from Python as well using, of course, the OS module again. And there is a special command called getcvd, that stands for get current working directory. There is also a command for changing the current directory called changedir, and that will also change the current working directory. So if you are going to, your Python code is going to change a lot of search working directories, it could be a good idea to start your code with querying the actual current working directory and storing that in a variable, like I do here. So here I store my current working directory, assign it to a variable, and then I can always change back to that when my code finishes. So if I run this here, let's see what happens. So here I see that I'm in the current directory, and I go up one bit, and I'm then in my root directory. Another common task is when working with computations and also with programs is the ability to actually query files in your directories. Of course, you can do that with ls, but sometimes you want to do it in a controlled way from your Python code. And there are functions for that as well. So in the OS library. So what you can do is there is a function called listdir, which will return you a list of directories, and you can iterate over them. And in this example here, I iterate over my directories and also query here using the OS path isdir to see if it's a directory or if it's a file. So there is a OS path is file, OS path isdir. So here I see you have listed all my files, and here I can also see that I have 2 directories only, so I don't have any files in my directory here. But it's a nice way to kind of query here. You can also, for example, have check the strings here for extensions and so on. So this is a bit more longer example here. The first part I do here is I assign my current working directory to a variable so that I can remember it. I have an if statement here, so if OS path exists, that is also a function that you can check for example, if there is a file or path, you can query if that is correct. If it's not there, you can do something. If it's there, you can do other stuff here. So in this case, I check for a directory called OS5, and if it's not there, I create it. Next part I change into that directory, so the current working directory is OS5. In that directory, I create another directory called testdir using the makedir function. Then I open a file for writing and write something to that file. I list the directory. I can rename my file using the OS rename. And then I list my directory again, and then I can remove the directory and the files here. So let's see what happens here. So you see here, it prints out the directory here. So you see it created a file, and it removes the directory again. So next time I list file, nothing is there to do anything. So this is a way. So instead of calling system commands from your Python code, you can actually do most of the system commands with functions that are built into Python. There is other ways of actually querying in more detail for directory and file information, and that is using the OS scandir command here and iterating over this. So in this case here, for entry in the iterator I get back from scandir, then I can print out the entry here contains name, path, and also methods if it's a directory or a file. So here you can see here I have something config, what the path is, and I can say this is the directory, this is directory, and this is also directory. So it's basically a bit more detailed, just listing the files. You can also walk iteratively through directories. So if you have a tree that you want to kind of go through, you can use the walk method to use a for loop to iterate over directories in all the files in a directory tree. So if I run this here, you see here that it goes through all the files and prints out all the information I have in my directory here. On Unix machines, you can also, there is a command called stat where you can get even more detailed information of files and directories. Please note that this is only available on the Unix platform, so that is Mac OS and Linux, so not Windows. I just want to show it here because on the Linux platform it can be quite important. So here you get back mode files, UIDs, size, modification times, and a lot of detailed information. And for more information, look at the documentation for these functions here. I think so. Also, you can also, one thing that is often important is that you need to combine directory and file names into paths that you can open files. And it can be somehow tricky sometimes, especially if you're working between platforms where the notation of paths are a bit different. So there are a multitude of different functions for doing this. So the first three here, these are basically to get more information from your existing file path. So in the base name here returns you the file name. And the dir name will return you the directory part. Also, if you want to have the absolute path of something, you can use apps path here, and it will take a path with special characters in it, and it will expand those to the fully qualified path name. Path exist I showed you before. There's also this way, if you want to expand the user, if user gives you this home path on a Unix machine, there's a special function here that can expand this to the fully path for the user. You also have get A time, get M time, get C time for access time, modification time, and creation time of a file. You can get the size of a file. You can check if it's an absolute path, that is, it's a complete path, not a relative path. You can check if it's a file, it's a directory, which we did before. And also, there is a very useful function called join. We will take a directory and the file name and combine them together into a file path, and that it will do this platform independently. So it can handle Windows path and it can handle Unix path at the same time. And you will get back a path that is useful on your system. There are also some function here for splitting file paths, splitting drives, splitting extensions. So let's see what happens here if we run this. So as you can see here, let's see here, no absolute path, it's a file directory, but you can also, this is the joining here. So it joined the things together. Here you can, the split here will split the file into the path and the file name. And then you can split to drive, and it doesn't work. I think it works on Windows only, so this is a bit bad example here because we are running on a virtual machine that is a Linux-based machine. I have skipped, there is an object-oriented way of combining path here, but I skip over that because it's a bit hard to use. But you can look up it here, and it's powerful, and it will return you a system-independent path. Temporary files. Temporary file sounds somewhat simple, that you just create a file and then you delete it. But many of the security issues we have with files today is actually when you create files temporarily in a way that is that is visible for other users on the machine. So Python contains actually special functions for creating secure temporary files. So there is a module called temp file, and temp file has a function called make secure temp, and it returns you a file path and also where it's located. And then you can use that to open it as a normal file and work with it, and then you can remove it later on. Let's see what happens here. So you see here it creates a temporary file in the temporary directory automatically, and it creates a unique file name. And then you can use it like a normal file. And afterwards it will be removed here. So in this case, you have to remove the files yourself. It's created in a secure way, but you are responsible for removing it. There is also an object that you can use called temporary file that you can use as a normal file object. And the nice thing with this is that it will automatically delete the temporary file when you have used it. So if I run this here, you see here that after this with statement here, I haven't deleted the file into my code at all. So if I ask for the temporary file name here, this will not be, you see here, it doesn't exist anymore. So it automatically deletes the temporary file if you don't use it anymore. And temporary files could be, for example, if you have computational codes that need to write a lot of files that you don't need after the computation. Temporary files can be an option, can be a way to kind of do this without leaving a lot of files around. Another thing that a common task that you often use in your code, especially if you're using Python, because Python is very good at language for kind of gluing together stuff. So when you want to control other programs from your code, and there's a lot of ways of actually, you can start Fortran code, C codes, binaries from your Python code and control the execution of it. So one module that is common to use is the sub-process module, and it has a lot of methods for executing commands. So in this case, I have a run here. The first parameter here is the ls, which is the listing files, and la is the options I want to specify to the code. And if I run this, it returns your return code if everything worked. Please note that this didn't return any output because process run will not return any output. If you want to have output, you need to add some parameters here. So shell true here is that it allocates a terminal shell that with the environment of your code, and it will use that. And subprocess pipe here will kind of get you piping to kind of get the output from your code, which you can actually query later on to get your results. So in this case here, I get the result here, and I have my return code, but I also have my result standard output here, which is the output from my code. So here I have just listing the files in my current directory. So you see here standard output. The output from ls goes into this variable. Sometimes you need to know when the execution of your process has finished, and you do that with the method. So when you execute something, there's a special method called popen, which will return you a process object. And that process object has a lot of methods for kind of checking for output. I have an important phone call, so I just stop here. Right now, I'll get back. Okay, sorry for that. Repairman here for our water cooler. Anyway, so this process object enables you to kind of wait for the process to finish. You can also start the process and do some other stuff in Python, and then call the wait method here to actually wait for the process to finish. So in the other call we did with the run, that will not return until the process has finished. So with subprocess p open, you can actually start something, do some other processing in Python, and then wait for your process to finish. This is what we do here as well. So we can do process open here, and then we sleep 5 seconds, and then we have a function here to check for if the process is still running, and if it's not running anymore, it will exit, and then it will return here. So in this case here, you see here the code is waiting, it's waiting, and it returns 0. So in this case here, we started the process and we kind of pulled for it, waiting for it to continue, to terminate. There's a lot more you can do here. You can get standard output, you can get standard error as well. So now we're waiting here. So now also we did an ls here and outputted the directory listing here as well. Skip this one here. Sometimes it can be a useful thing to kind of combine this to a single command. Often you want to execute a command and get the output back. So here I've created a function here called execute with output, and it will do all this stuff. We can also use the with here to make sure we close all our open files, and then we'll return the standard output out to the function here. So this makes it a bit easier to use it here. So I only have to call output here and execute with output. And if output is not none, I do the splitting of the lines and then print output here like this. Sometimes when you have larger codes, you often, computational code, you use the print statement to print the kind of progress of your code. The problem with the print statement is that it's not buffered. So it's not certain that at that point where it's written to file, that it's actually at the same point in your code. And sometimes also it can be useful to get information about where the date and time for the things happening in your code. Also getting the warnings from your code that depend the kind of importance of a message. And this is what you can, so this is a very special module in Python called logging that actually can handle most of these things for you. So at the basic level, it just logs to your standard output. But the nice thing is that logging is not buffered, so it will write immediately to the standard output, so to kind of show you when things are actually happening in your code. You can also output different levels here. So I have debug for kind of messages that are only needed for when you're debugging your code. You have information that is kind of general information that is not critical. You have warning, error, and critical. And then you can filter the output here, what you want to see on the screen. Now I have to let the water cooling technician in, so one moment. So the water cooler is probably not running Python, so that's why we need service on it. Anyway, so this will output some logging. I'm not sure it will work here. We'll try. Yeah. So this is what you get output here, and so you see here the level, the user, the test message. You can also customize this in different ways. You can create multiple loggers. I will leave that up to you in this exercise. But here is something you can configure the format of the output here. So in this case, I have the time, name, level, and message. Okay. I never get this to work. If you run this on your console, it will work. It will not work in this notebook for some reason, I don't know. Okay. Some other nice features of the system libraries is actually you can store data, Python data, to disk in a very easy way, in a structured way actually. So there is a module called JSON. It stands for JavaScript Object Notation. So it's a way of writing information to a file that has the same structures actually as the Python data structures you enter in your code. So for example, here I have my data here. This is a dictionary containing a multitude of different elements of different types. I can open a file here, my data JSON here, for writing. And then you can use the JSON dump command to take my data variable here and write that to disk. And then you can, just to show you, you can use the load command to load it back to disk. So in this case here, you see here that this is my data here that I read back from disk. So it's very similar to, so I got back exactly what I wrote. And if you look at just the file that is stored on disk, it's stored in a very Python-like way. So JSON files can be used for configuring your code or writing things that you need to kind of be able to edit by hand. You can also, another interesting thing, you can actually take your data here and dump it to a string, and then use that string to get it back again. In this case, I have a JSON string here. So if I run this, it prints out the JSON formatted file here, and you can load it from a string as well. So for example, if you have a network, something that communicates over a network, you get a string, and you can take that string. If that is a JSON string, it can convert it back to Python data structure. It can also you can also dump it in a way that is more structured. So you get this kind of multiple lines. And you can add some options here. So sort the keys to kind of present the keys in a sorted order. You can also specify which indentation you want in your file. So this is, then you get this structure instead. So here you have a more readable way of your file. There's also another way of writing a file that is a bit more efficient, and that is using Pickle. So Pickle was actually in Python long before JSON, and it has the same kind of way of using, the same kind of writing the file. So you open a file, and then you can Pickle dump. And also note that we are using binary files. So Pickle is a binary version of JSON. So it writes your Python data in a very efficient way down to disk. And you same thing, you use the Pickle load here to load your data back from disk. So as here, I actually get back what I wrote to disk here. You can also write the data in different versions of the file. So if you have an older Python, you can specify which protocol here to use when you write to disk. Same thing here, you can dump the strings with dump s, and you can read back with load s. So the dump s, the s stands for string, and so basically it does all the same thing, but it uses strings instead of files. So the final parts here I will go through is how you can do data archiving and compression directly from Python. So the first thing, I will download 2 images from the web. So build 1 and build 2. And now I want to create a tar archive of these 2 files. So these are on my local machine in my current working directory. There is a module called tar file that is built into Python, and we import that as TF. So with tar file, and then I can specify here the name of my file as mytar, and then I can use the object mytar here to add my images to it. You can query, so you can open the file using read, And then you can get the contents of the tar file. You can get other things in here, and you can extract here. Extract image1 to my tar. And you can also extract all, and you can specify the directory here. So let's see what happens here. So it added things to my tar archive, and you see here it listed the files that I have in the file. If you look at the directory now here, I have a my archive tar JC. So what I can do here is I can also just I did something wrong here. Okay, but it actually contains the files here, so that should work. But now I have to restart my. Okay. Another thing you can do also is you can create zip files. So there is a zip file module. A zip file module here, which works in the same way as you do with the tar file. It's a bit different, but than the tar files. So for some reason they don't have the same syntax, but the basic functionality is there with extract all. You can write images to it, and then you can look at them. So I have a question here also: what advantages and disadvantages with JSON versus Pickle? So I would say if you want something that you can edit manually in a text editor, the JSON has clear advantages because it's pure text files. Pickle by default is binary. So if you want to quickly, for example, if you want to do a save state of your computation, you can Pickle more efficiently to disk. There are also functions in NumPy that can do similar stuff. So you have to decide a bit. But if you want to just make a snapshot quickly of data, I would do Pickle. And if you want to edit something outside your code or configuration file, use JSON. Let's see here. So here I actually archived and unzipped my files, and then I just display the image here. So I show that actually was something that was important. It's also possible to combine Pickle and zlib. So Pickle is not a super efficient format for storing files. If you want some bit more compression, you can actually use the zlib module in Python. So in this case, I create a string using the dump command. I print out the length to just illustrate the concepts here. And then I do zlib compress. So then I get back a compressed string. And then I do an uncompress here, and I load the string here again. So using this, you can actually compress your things. So you see here, the default length of my string here is 2,825 bytes. when I dumped it to a string, and when after compression it's 1926. So this is a way of kind of Python contains a lot of things. There are batteries here that can do a lot of stuff. So before using anything other outside your Python code, check your runtime library. It's there. Finally here, there are some other file format that can be useful here. So for example, the Windows introduced many years ago a special configuration file called ini files. Basically what those are is they have captions here that denote sections of your configuration here, which you can access by name. So in this case here, I open a file. I write this to a configuration file. I import something called a config parser. Okay, so I have a question here: what happens when a file is compressed? So I'm not a super expert in compression, but the idea is that you find things that are repeatable and replace those with some kind of token that says here comes 14 bytes of something instead of actually using the 14 bytes. There are different compressions. The easiest one is run length encoding, basically finding a lot of repeatable characters and compressing those to shorter commands that says here comes 14 A characters and now 3 B characters. And then there are other compression, but basically it's finding kind of the empty stuff and removing that and compressing it together. Then there are some image compression algorithms that are really complex that use fast Fourier transforms to kind of compress. But I am not an expert in that. But CLib is a non-destructive compression algorithm. So the config parser is a module that takes an ini file, it reads that file, and then you can access which sections are in the configuration file. You can access like a dictionary here. So I want everything in my big bucket. I want the user configuration variable here under big bucket here. So see here you can get out all the information from this configuration file. There is also a CSV reader that you can use that will read comma-separated files. It's not super easy to use. Sometimes it's easier to actually write the comma-separated files yourself. It's a very simple file format, but this will help out in some way to create these files here. I need to get those. Let's see. And then you get out, like, you can read in and you get lists here like this. So, any more questions on this? So I suggest we take a 10-minute break, and then I will do the object orientation part after the break. So we'll be back 2:05. Okay, so now this course, as I said before, will not teach all the concept of object-oriented programming. It will give you an overview of what's available in Python and kind of what the concepts are about. Because Python is, you probably noticed it already, you are using objects all the time. So when you create a string, that is a string object, and we already call a lot of methods on that, which is, for example, split and so on. So what is object-oriented programming? So object-oriented programming is the concept of an object that combines data and method into a single entity. So in many function-oriented programming languages, the functions are the kind of where you pass the data to a function to do processing, you get the data back, and you pass it to another function. So there's a separation between data computation. So in object-oriented programming, objects often describe nouns. So for example, point, circle, equation, model, square, particle, etc. These are typical objects that you kind of want to work with. You interact with objects by sending messages. And the messages are also called verbs in some way, or methods. So if you want to, for example, if you have a string and you want to tell the string, I want you to return me the split here. And then the string will return and do that. So that is a verb. You tell the object to do something, and that is a verb. So an object typically has methods which define what the object can do, the verbs, and properties that describe the attributes and links to other objects. So for example, the data is often stored as attributes in the object. And in Python, you describe objects using something called a class. So a class is a blueprint for an object. So you basically, in Python, you describe, this is how I want my objects to work. So the class in itself is not an object. It's just a definition of how the object will work. So I will try to share a different screen here just to kind of make it a bit more clear. So I'm not sure. Can you see a white screen with the object-oriented concept on it? Okay, good. So so the class, as I said, is the blueprint for the object. So here I have. Oh, I didn't want to do that. So here I have a point class. So this is the class definition. So this is the point of an object that is named based on a class point. And then we have the data, that is the attributes. Those are also defined in the class. So if you have some default values, those are stored in the class. And then you have methods of verbs to tell the objects to do something. And in this case, this is, for example, move. So you can move your point on the screen. You can set the name of the object. And a nice thing with objects is that when you create an object, you can create a new object that inherits all the properties of points. So in this case here, I have the circle class that inherits all the attributes of the class point, and you add radius and set radius method to it. So you can kind of build up a generic functionality, and then you can add more functionality to derived objects. Another thing also that is important to know, that, as I said before, a class is just a blueprint of an object. So when you want to use an object, you need to create the object, and that is called instantiating object. So in this case here, I have my point class here, and I create a P0 here. That is my variable reference in Python. And then I create a point object here. I will show you exactly how that's done in Python here. So this will make a copy of the attribute data, connect that to the point to P0. I have also a P1 here that also an object of the class point, and then this will have its own set of data. So the data, when you create an object, what is copied or created is the actual data for each of the new objects. So they will be completely separate from each other. So the data defined in your class is not shared. So that is only used for kind of creating new objects. Then of course, when you have all your variable references, the methods themselves are actually stored together with the class. So you have move method here, and all the Python methods, they have this self parameter. And when you use an object and you call a method on an object, the class method will be called with the self actually containing the variable reference. So self will be replaced by the actual object when you implement your class methods. So that's why you have this self. I will show you this in code later on here as well. You can also create more complex objects by combining different objects. So here I have a line class here. It has a point array here, which will contain points. You can set the points here using a special verb, and it will have 2 instances of points here. So that is a way of creating a line class that can handle 2 points. So then line will own these points and manage them. So this will be just a graphical description on this. So let's see here. I will try to. So I will try to illustrate everything here, but by first showing a function-based version of the same code I will show you later on as object-oriented. So in this case here, I have functions here. One create point will return you a list with 2 x and y coordinates. I have a move point method here that will takes a point reference and move that point reference manually. And also here I have a 0 point that will zero the contents of the point to 0. I have a set point here that will assign new values to the x and y, or the point data structure. And then I have a print point here. So this is a typical way of doing this in a function-based programming way. So in this case here, I create a point like this, and then I use my print point to print. And everywhere I go, I pass along this p, which is my data structure. And the functions modify this data structure. Every time I call those, I pass along the p, I print it out, I set the point, I print the point again, and print the point again. So here there is a clear separation between functions and data. So data is just passed along the functions. With object-oriented programming, you try to combine this together. So in this case here, I create a blueprint of my class point that will be able to do the same thing, but in this case, every time you create a new point, the data will kind of follow along. So in this case here, I have a new class called point. I have there is a special method here that is called every time a new object is created. The underscore init method is called. It's also called a constructor. So and that is responsible for setting up the object for use. So the responsible for that is to kind of create the data or attributes required for the object. So in case you see also the self here, self will replace with the actual reference to the created object. So every time you see a self, you have to think this is a pointer coming in that will be used. That is the actual object created. So that's why, because you have this is a template, so you can't actually get the actual pointer over. So you have to have something else, and that is called self. So self is now attached to the actual object reference. So now I can use this here. So now I can create new objects from my class definition. And you create new points by choosing a variable name, assigning a new point instance here. So in this case, you have the class name you want to create. And then you have a parameter list here. And now it's empty here because you never have to think about the self parameter. So in this case, self here in the constructor has no parameters more than the self in itself, and then you don't have to call that here. So, but you can have more parameters after the constructor here, and then you specify them here. But in this case, we have empty parameters. So now we have two instances of a point object. So in this case, P and Q. They are completely separate, so they have their own data. And in this case, it's a bit difficult to see because they all have been initialized to 0 here by the constructor of the object. So this here will call the constructor for the object. So it will, P here will become the self parameter going into this one here. And self will actually set X and Y attributes on this object. You can also assign the attributes like this. So p.x equals to 1 and p.y equals to 2. And then you modify only the one that you assign the attributes to. So if you come from other languages where you have object orientation, this way of accessing and also assigning attributes is against the encapsulation principle of object orientation. That is, you should never access the attribute directly. But as we will see further along, this is not a really big problem because Python has a way of kind of transitioning into this method of working. But if you want to do this class completely correctly, using the way you should actually do the encapsulation in other languages, is that you have to declare your attribute as private. So in this case here, I have add two parameters, X and Y, and I assign a private attribute to my class here, and I have two underscores here. That means that those are invisible to, you can't access them outside your object, so they are protected. So now I instantiate my P object here. I didn't forget to run this one like this. And now we try to access the attributes in the class here, and we will have a problem here because there is no attribute X anymore, because we have now two protected attributes, X and Y, but they are not accessible from the outside. So to be able to access those, we need to create methods of accessing them. It's also not possible to access the underscore attribute. This is kind of prohibitive in Python. So by adding underscore, you actually make something private to the object. So this is the way you do it in normal object-oriented programming. You have you add methods for setting the X, setting the Y, and returning the value. So in this case here, I have set X, set Y, and set here to make it. I add those to the class, and now I can assign my attributes by calling these methods here. And also now the user can't access the internal workings of the class, and that is one of the key concepts here, that you encapsulate the implementation of your class. We also need to add methods of actually returning the values of X and Y. So I just add X and Y here instead. And those will just return the internal attribute values to the outside object. So now we have an object that we can access. We can set the attributes and we can get the attributes here. But now this object could have been implemented. Instead of using internal attributes, you could have a database server somewhere that actually stores the X and Y, and the set X and set Y will call the database and store the values, and when we retrieve the values, it can get the values from a database. So by using the set and get methods here, you can encapsulate internal implementation of the object. The reason I say that Python has a sliding, you don't have to do this directly. You can work towards this. Is that there is a concept of Python properties, and properties is a way of emulating the easy way of assigning attributes by assigning them directly on the object. But instead, when you assign, you call a set, and when you retrieve something, you call a get. And in this case here, I have all these set, and I have my get y and get x, and I can easily create a property here, x equals to property, and then I have get x and set x. So when you access the object to return the value x, it calls the get x, and if you set something, it will automatically call the set x method. So this is a way of combining the benefits of attributes directly accessible with your control over the implementation. So now we can do this instead. So instead of calling all the setter and getters and this method, you can actually just assign p.x equals to 42, and I can access them just like they would be attributes directly on the class. And you can see here that it calls all these methods here behind the scenes. So I have a question here. So init is actually a function, a method that you need that will be called when you create the object. And self are kind of a dummy variable that is used to be able to reference the actual object values when you create the implementation of the class. So otherwise it's impossible to actually define the behavior of the class if you don't have access to the self. So self is, when you code, self is the actual object reference of an object instance, but it's passed along transparently, so you don't have to actually pass it along when you create an object. It's handled automatically by Python when you create objects, but in the class definition you need to have the self to be able to access them. So instance methods. So now we have looked at attributes. We have already looked at methods as well, because the set x and set y are methods, but there are methods to access the attributes. Sometimes you need to, for example, if you want to move the point here, in this case, you have dx and dy, and then you can modify the internal attributes and move the point. So this is my method here, and then we can use, for example, I can create 2 points, p0 and p1, and then I can move them here like this. You see here that it added 5 to this, so it's subtracted 5 and you get a new position of the point. Another nice feature is that many times is that you have an existing object and you want to copy over the values to a new object. So you can create a copy from. So here you have a copy from method here, which takes one parameter here, which is the p, and p goes in here, and then you assign the attribute x and y, internal attributes, the object attributes x and y. So basically you copy over the values. And here I have same thing, I have p1 and p0, and I copy p1 from p0, and now they should be the same. Let's see, now p1 is the same value as p0. So it's a way of, so that's one nice method to implement on your object. There are some special instance methods available to you as when you define your classes. We have already seen one of them, and that is the init method, which is called when you construct a new object. So every time you construct a new variable reference to an object, the init method is called. And the init method is responsible for creating the attributes, internal attributes, and set up the object, basically. There is also a special method called str, which you can use to create a printable form of your object. And you can see here, if I create a point and print that point, it will just dump out the kind of internal representation of my object instance. But it's possible to create a printable you can create a printable representation of your object using the __str method here. So in this case here, we add this method here, which will print itself. It will return a string that is represents prints out the object's representation in a kind of more logical or pedagogical way. So let's see here, we define the class again. And here we use the same print here, but now we have this string method here. So let's see what happens. So now you see here it prints out a much nicer representation of your point. And what happened is that the print statement actually always calls the str method of any object that it sees, and then prints that out. Classes in Python are, your own classes you create are basically equivalent to the built-in data type. So you can use them exactly the same way you use any data type in Python. So for example, here I create 10 random points and I add them to a list. You can do it like this as well. And then I can loop over this. So for p in points, I can print out the values here. Now, because I have a print statement, str method on my class, I can get a nicely formatted output of my objects here. So I just call print p and it will call the str method of my own class. And also reference to objects work exactly the same way as for normal Python objects. So in this case, I have p2 equal to p0 and p3, and those should be the same references as the other two. So p2 and p2 should return reference to p0, and it seems to do that, and p3 as well. So basically, when you have defined your own classes, you can use them in dictionaries, you can use them in lists, you can use them in NumPy objects with pointer references and so on. So it's very powerful. So inheritance. So suppose I want to extend my library here. I just don't want to write points anymore. I want to do some more stuff. So what I can do then is I can use inheritance here. So I say that I want to create a circle, but I want to have all the attributes and methods from my point. So then I create a init here, and I will use the same parameters as x and y as input. And then I also add my radius here, because that is the differentiator with a circle. Now, the first thing I have to do in my constructor is actually call the constructor of point, because if I don't do this, the x and y, the constructor of point will never be called. So I need to kind of call that constructor. And there is a function in Python called super, which will return you the derived or the parent object. So you don't have to explicitly state which object you call. And then you call the init method of that object. So now point attributes have been created. And then I add my own attributes here. So my radius, I will add that. And then I will create all the methods here I require for accessing my data internally. I also create another string here, because if you don't create a string, the str method of point will be called instead. So now I can actually create my point, create my circle here. I set the radius to 10, because this is a property, so that works perfectly. I can move my point, I can move my circle using the same method as I had in my point definition, and I can print them both out. So, and that will look like this. So now you see here, Python knows which str method to call. So it knows that it was a circle, and it called the print str method of the circle instead. I showed you the way you can create classes with which has components or is composited by different classes. So suppose, for example, we have a line that goes between 2 points. Then we can use 2 points as the references to these points. So in this case here, I have a class line, I have a constructor here, and I have two internal attributes as a p0 and p1, which I instantiate to point here. I create my normal access methods here. And then I create my string here to print it out. And then I have two properties here, p0 and p1, that returns me the references to p0 and p1. And now I can use this line like this. So I have line p0.pex equal to something, and I can access those attributes and properties from my point instances. I forgot to access. Okay, yeah. The thing is here, the reason I get an error here is that I have decided that I only want to provide a property with a read possibility. So in this case here, if I try to assign P0 here a new point, that will not work because there is no set method here. I can add set P0 here, which I have, like this, and now this code will work. I haven't defined it yet. So now in this case here, now I'm allowed to assign the object reference, the variable reference P0 with something new. So properties can control the way you access objects. So if I remove this, the access is read only. You can access the variable reference and you can change the properties X and Y, but you can't reassign the variable reference. So that is one of the reasons we have properties, to be able to control access to your internal attributes in different ways. Yeah, here comes the example here, so I don't want to run this again here. You can of course add a method here to calculate the length. So in this case I have my calculate length by calculating square roots and so on, and add that as a method. I'm too quick a bit today. So now you should see here that you can use the length here as well. We could have done a property here as well. So in this case, I can do length equals to property, and then I use I have to modify here get length. Then we can do like this. Like this instead. So now we can use this as a property. So this is a way of providing easy to use functionality of your objects. The final concept I will talk about is something called polymorphism. And what that means is that Python knows, or it's a way that, and when you have a lot of object instances, for example, in a list, Python knows how to call the correct method depending on the type of the object. So for example here, I have a point circle on a line, and I also have a value I just put in here for an example here in this list. And what polymorphism enables you to do is you can iterate over the shapes, and you can print all the shapes, and the print method will call the correct versions of the str method on your objects. So in this case here, it will call this different str method in my code. But the interesting thing is how did this work? So 42 is a floating point number, and you can still call print as a shape. So the interesting thing here is that in Python everything is an object, and even the floating point number is an object. So this is what actually happens in the print statement. It calls the str method of the floating point value. So this is perfectly legal code in Python. So you see, everything is an object. So as a finishing example, I will try to do a bit more complex example. This is the first time I'm doing it, so I hope it will work, but I will try. So just a comment on the object orientation here. So when you do numerical codes, you need to, it's tempting when you have object-oriented programming to implement everything as an object. For example, if you have a particle system, you have the nouns are particle, you have a particle system, perhaps you have a bounce or something, and it's tempting to create a particle object, particle class that contains position of a point or a particle. And then you create 1,000 particles and you put them into lists and then you iterate over them. The problem is that you will, for every particle you will create new memory references that are new memory allocations in memory. And for larger problems, this is really extremely inefficient. So when you want to do object-oriented programming in numerical computing, you should always think about working in larger blocks of data, for example. So you should, instead of having a particle, you should have a particles class. And that particle class will use NumPy to create a table of positions for the points of the particles, for example. And then you will work on the chunks of memory that these NumPy arrays are. And those are much easier to update and also much more efficient and fast to update than updating a single particle in a list or array. Just keep that in mind. And now we'll try to see if I can find my other share here. So can you see a code editor here now? Let's see here. So my idea was to make a simple particle system here. It will bit more. It will be a bit copy paste, but I will try to make it so that it can compare to how you will implement it anyway. So the first thing I usually do when I do object-oriented programming is to kind of figure out what classes do we need. So for a particle system, as I said before, I will need a particles class that will store all my particles and also perhaps initialize them and update them in certain ways. Also perhaps some attributes to access them. I will also, in this case, I will first do an implementation without any properties, without any getSet method, and then we'll add these attributes to the class later on. So particles is one candidate, and then we have a particle bounce to kind of limit the particle's movement. Particle bounce, so that will be one class. And then I have a particle systems class that is actually that will contain the actual algorithm to actually move the particles around. So I have three classes here. So I will start with a particles class. And then we need a constructor. I will have a parameter here that will give a default number of particles. So I put 10 particles here. It's a very small particle system. Then I will need to have positions, and I also need velocities as data attributes for this class. So I will create self pulse equals to I need to have some import modules here as well. So we will use NumPy, we will use matplotlib for displaying the particles and some animation clauses. I don't exactly, but so then I create 2.0 times np.random.rand n rows, comma 2 columns. So this is a two-dimensional particle system. Self.val equals to np.zeros n, comma 2. And then I initialize here using, now I will copy and paste a bit here, but the magnitudes of the velocities and angles here, I will create random angles and create them in different directions here and store them in the velocity class here. I will also try to avoid using any loops in this code. So I will try to use the arrays directly without any loops, because that is the most efficient way of using NumPy in any way. I will also add a special method here called count so that we can quickly access the number of particles we have in the class here. So in this case, I return shape 0, which is the number of rows. So that is the number of particles. So now I have my particles class. So this basically is just a container of the positions and velocities and initialization of the particles. Then I will implement my particle bounds. Now it will be a bit copy paste here, but so this class will have so basically just the box where the particle will move. So they will bounce on the box side. So the left side will be at -1, right side at 1. Assign some internal attributes here. Please note that I'm not using any properties. I'm just using directly attributes. So there will be no get and set methods in this case. I will show how to add that hopefully before the lecture is over. So next thing, I need to have a method for checking the bouncing, or if the particles are bouncing towards the sides of the bounce here. So this will be a lot of copy pasting here. So I have a method called check. So all methods we define needs to have a first parameter called self. You will never call this parameter by yourself, but you need to specify it when you do the class definitions. And the parameters here is an instance of the particles class and the time step here to be able to modify some things here. This is not a very good particle system, but it's just an example here. So now I copy a lot of code again. So this is an example of how to implement this without doing any loops. So in this case, I create, I check for if the particle positions are less than left. That will return you a logical array that is true or false depending on how this condition will be set. So I also convert these. I create a special multiplicator here with ones, the same size as the particle system, and I also assign these values here. So if if they are outside, I assign -1. If they're not outside, they're 1, and then I just do multiply here. If they're outside, I move 1 back and then assign a new value here. So you can figure. I will just show you how it is done object oriented. So now I create the main class, the particle system class. So in this case here, the constructor has also an n parameter here to kind of let the user be able to create a new particle system. And I set 1000 as a standard here. and I self n for n particles. I assign the n value here. I set the time step value to 001. I create my particles instance here and attach it to my object. I create a bounce object here and attach it to my object here as well. Next, I need an update method to kind of update the time step of the particle system. So I just add an update method here, which has a time step also. And then we update without looping here. So these are arrays, particle position array. I add that together with itself and the velocity times the time step. So this is a non-looping way of moving forward in time without any loops. Also, to be able to plot here, I need to do some setup here. This is a bit... so I create a figure in Matplotlib. I create a scatter plot to plot the particles here. And I also set up a special animation function here to update, animate the plot. And the update here, the update plot is actually where we will do the entire run of the particle system. So here I have the I here. I don't know. We don't need to care about that. But we set update the scatter plot by using self-scat set offsets that will set new positions for the points of the scatter plot. I will move forward in the simulation, and I will check for bounces with the walls. And then I will add a method to my particle system that will start everything off. So I have a run method here that will start a simulation here. So I have setup plot and plot show that will show the window, so we can show. This will not work in a Jupyter notebook, so you need to run this as a separate code. So now I need to just create my main program. We have all our classes defined. I do if main equals to if name equals to main. So the first thing I need to create is my particle system. So I do particle equals to particle system, and I start with 50 particles. And now I can do like this. I can do partsys.run. So this is the, let's see if I have, see if it works. But now I'm not sure it will display here. I will just stop share screen. Okay, so I run this again. I'm not sure here. Okay, it's. I think it's a zoom animation here, but you can see that the points are moving. So what you can also do with this new notation here is that you can do stuff like this. So you can create your own bounds, object particle bounds. Minus 2.0, bound.right equals to 2.0. And then I can also create my own particles instance here. And I say I do 500 here. And then I skip this one here, and then I partsys.particles equals to particles. And also partsys.particles sys.bounds equals to bound. So in this way, I can create my input here in a way, and I can control my particle system by assigning different properties. And that should also work here. Now we should have 500 points. It wasn't this slow when I run it my computer. I think it's the Zoom thingy here. But at least you can see here that it moves around here. Now there is the bound is 2 now, so they will move over here before they bounce. So you see here that you can start off doing object orientation in Python without thinking about the get sets or properties or anything, and then you can transition into this way here. So for example, one way of using properties would be to make sure that the bounds are correctly assigned. For example, that the left side is less than the right side, for example. So we could do, let's see here. So what we do first is that we modify the current internal attributes here and add them as private here, like this. Then we add properties here. And now I will show a much easier way to create properties. So there is a special, it's called a decorator that you can use to automatically create properties for you. So in this case, property, and then you create define, and we have left, self, this will automatically, so now by using this, you can use the left method. There is a property called left, which you can use exactly the same way as you did with the internal attribute. And you can also do left.setter, which will also create a assignable property. So in this case, I do self, comma, left here. So just create a method that will assign this one, self.left. So this will work. So now, in this way, the use of the code can be the same. I don't have to change anything in my code, and I can add checks to the attributes automatically. So now I will try to copy the code here, so I don't have to do it wrong here. I will. So what I want to do is I will add checks to these properties here. So now in this case here, I have, I will do it when I assign the left side, it will check that it's less than the right side. So it has built in, so you can never kind of assign things wrong in this case. And the code will work perfectly fine now. So now I can run it again, and it should work without any error messages. So it works perfectly fine. So what I only did was I changed the internal attributes to private, and I added my properties using this decorators here property. And of course, you can do the same thing for these ones here. So you could have a particles instance here that is a property of my particle system and so on. So this is a way of enhancing your first implementation of your sketch to be more robust. For example, you could have only a get property for the particle so that the user can't overwrite existing attribute or variables that are in the class. That is, of course, a choice you have yourself, but that is a way of you start sketching something quickly and then you add more functionality to it. So that was what I wanted to explain here today, and I hope it did make some sense here. And I will try to provide a code for this as well, so you can try it out yourself at home. So I just want to introduce you to the object-oriented way of Python, how Python works, so that you don't, when we go to the next lecture, which is user interfaces, you will use a lot of objects, and it's good to know how to have this kind of conceptual model of what object-oriented programming is. So, any questions? I have a question here from regarding the data types in NumPy. So the D type is available as an attribute on the array object. So you can query the current the data type that has been for the created array after that has been created. And you can specify, I think, is float 64 and float 32 as well as data types. It can be a bit daunting to kind of first time you see object-oriented programming, but experiment with examples in my notebook. Also, I will let you get this particle system code as well that you can experiment. I will give you one version that is extremely object-oriented and one that is the version I showed you here, which has no properties and no get-set methods. So you can see the difference in the implementation. And also look at how you can think about array programming in Python, because the key for efficient code in Python is not using for loops at all, except for on a high level. If you're working on an outer loop, for example, you can use a for loop, but you shouldn't loop over particles, for example. You shouldn't loop over individual X elements. You should always work on array objects. It's very similar to what the recommendations is for MATLAB, for example. They also want you to do array computation instead of looping. So I don't see I can see any more questions. So otherwise, there will be a tutorial on Friday, and I will hopefully I will have grade all your assignments until then. So there is a lot of them now. So thank you for the submissions. Okay, thank you very much. See you on Friday.